All right, so let's look at an application of the central limit theorem in roulette. Okay, so roulette is a game that there's a ball, so we have an American roulette wheel. So American roulette wheel has 36 numbers. So it has numbers 1 through 36. It has a 0 and a double zero. Okay. And we'll call a bet the house special. This is a bet on the basket. Doubles 0, double 0, 1, 2, or 3. And it pays 6 to 1. So if you put up $1 and it hits, you get your original dollar back plus $6. You profit $6. Let's assume that we spin the wheel 10,000 times. And with a $1 bet, each time, what is the house's, meaning the casino's, expected gain? How much do they expect to win off of this bet over 10,000 and over 10,000 roll spins? And let's approximate the probability that the house wins more than half of that amount. So if we were going to do this if we were going to do these calculations exactly, what would happen is we'd have a hard time because the discrete nature of this means that there's a very it's an intractable problem, and that's where the central limit theorem comes into play. So how do we set this up? Well, to set this up, let's let xj be our win on the jth roll. So we either, oh no, the casinos win on the jth roll. So the casino is either going to win $1 33/38 of the time, because there are 5 numbers in our favor. They all have equal likelihood of happening. So there's actually 33 numbers in the casino's favor. And the casino is going to lose $6 5 out of 38 times. Okay. Then we can actually write this as, we can observe that xj can be looked at as 1 minus 7 times yj, where yj is a Bernoulli random variable with success probability 5/38. So it's good for you if you're not sure where that comes from. Take a minute to think about where that relationship comes from. And then the net gain of the casino in the 10,000 rolls is the sum Sn x1 up to xn, where n is 10,000. And for a single spin, the expectation of x1, we can calculate it very easily. Well, x1 is the expectation of 1 minus 7 y1. This is 1 minus 7 times the expectation of y1, and the expectation of Bernoulli is just the parameter. So it's 1 minus 35 over 38. 3 over 38. The standard deviation of x1 is a standard deviation of 1 minus 7 times y1. Well, the constant, the shift doesn't matter, and the 7 comes out as a 7, not a -7 times the standard deviation of y1. So it's 7 times the square root of PQ, where P was 33 over 38. It's approximately 2.4. So then for 10,000 spins, what can we say? For 10,000 spins, the expectation of the casino's expected win is 10,000 times the expectation of its win on one spin, which was 3/38. So this comes out to be about $800. And the standard deviation is also just 10 is 100. It's the square root of 10,000 times the standard deviation of x1, which we calculated to be 2.4. So this is about 240. Okay. So this is the expected win. And now what we're interested in, well, what's the probability that the casino, after 10,000 spins, wins more than half of its expectation? Half its expectation is 400. So what's the probability the casino wins at least $400? Well, we use the central limit theorem here because we have a finite mean, we have a mean, we have a finite variance, and we have a large sample size. We have to subtract off mean and divide by standard deviation. And so this is equal to the probability by the central limit theorem. So this is not CLT, this is standard. But then this is by the CLT, the probability approximated by standard normal being bigger than minus 400 over 24, right? Minus 5/3, which we can approximate by, well, this is equal to 1 minus pi, the CDF of the normal 0, 1 of minus 5/3, which we can approximate as it's approximately 95%. So the casino has about a 95% chance of being up more than half of its standard of its expectation after 10,000 tosses. And then in general, for a general application of this, the probability that SN is larger than mu n over 2, probability Sn minus mu over sigma n bigger than or equal to mu n over 2 minus mu n. Sorry, I should put so mu n is actually just n times mu. So I'm gonna do this. Over sigma square root of n. which is approximately, by the central limit theorem, one minus the probability that a standard normal less than or equal to minus square root n mu over 2 over sigma, which converges to 0 as n goes to infinity. So or to 1, I'm sorry. Converges to 1 as n goes to infinity. So in other words, what happens here is that we notice that the expectation grows at rate n, so it scales with n, whereas the standard deviation scales with square root of n. And so the standard deviation is growing slower, much slower than the expectation. And so eventually that the expectation overtakes the standard deviation to where it's very, very unlikely. And as n goes to infinity, that probability goes to 0, that it's extremely unlikely that the house would win less than half of its expectation. And it's in fact virtually impossible for large values of n. So this is a very clear application of the central limit theorem. This is one of the, we can apply this much more generally. This is in the case of roulette, but by the nature of the theorem, it's widely used. It's really indispensable in statistical application, and it's something that just continues to come up over and over again. So it's very important to understand what the central limit theorem is and how it can be applied.